Morning.
Morning, teacher.
Morning, teacher.
Morning, sir.
Morning, teacher.
Morning. Who is reconnecting? As in, who has the username reconnecting?
Edmund, teacher.
Oh.
Morning, Joe.
Morning,
Morning.
teacher.
Morning. Okay, so good morning, everyone. Let me just quickly type today's attendance. So Cedric, CK, Daman, Diksha, James, Justin, Kezia, Mushiga, and Xenia. Who's still not here?
Joe, I hear it. You didn't.
Oh, hey, I didn't see your name. Oh, okay.
Yeah, poor reconnecting, you know.
Yeah, I saw. I was wondering, was that a name or was someone actually reconnecting? Okay, who is not here yet? And your friends?
Desiree,
Desiree?
Young Home, I think.
Yeah. So Desiree, Young Home, anyone else? Nikita is not here also, right? Yes, she's not here yet. Okay. Okay, we'll start first. Okay, before that, how is everyone doing? Are you all surviving well?
No, Joe.
No.
No,
Stressful.
stressful. Why is it stressful? Or what's stressful?
Well, work and also exams for the end of the year, plus a lot of bloody house chores I have to do.
It's okay. We shall go through this together. You all prefer studying at home or at school?
School.
Cool.
Why school?
For me, it's home.
No,
So, because we've all been at home so long, I think we'd be happier studying anywhere.
Okay. Okay. It's okay, guys. It's a new era. It's a new way of doing things. Y'all will be able to adapt to it sooner or later. But hopefully we can go back to school lah, okay? You have to stay at home and look at your laptop screen the whole time. Okay, so today we're going to do chapter 23 of your book, which is the last chapter. There's quite a bit of things to cover, but hopefully we'll try to cover as much as we can today, okay? This is on page 318 of your textbook. Okay, so let's start. Okay, so we're going to look at structure and properties of an atom, which is basically what we saw last week. We're going to do a recall on that. And there are three types of radiation. So we're going to look at the three main types of radiation. And we're going to try and explain the structure and properties of these radiation. Okay, so we're going to focus on three main types of radiation. Okay, a little bit of recap. So we look at atoms, and inside atoms we have particles. As we all know, we have electrons orbiting the nucleus, the moving ones, the nucleus, and then we have the protons and neutrons found in the nucleus. Okay, this is what we looked at last week. Okay, so we have proton and neutron with relative mass of 1, and then electron 0. Okay, there are usually equal number of protons and electrons. Why? Because one will carry opposite charge. One will carry positive and one will carry the negative. They have equal number of both, so they cancel each other out. So we get a balanced or neutral atom. Okay, this is we're looking at a stable atom. Yes.
Joe, will you post this later
Maybe. Why?
to take notes?
Oh, you want to take notes? Yeah, should be. Yeah, usually I will post it lah. Okay?
Okay.
But if there's anything specifically that you want to take down now, you can just stop me. Okay?
Okay, Chair.
Okay, so let's look at this atom. Is it stable or no?
Stable.
Why stable?
No.
Equal
Yes.
number of electrons and protons.
Oh, right.
Correct. So it's stable because the number of protons and electrons are the same. And what is the mass number?
5.
5. Why 5?
3 protons, 2 neutrons.
Correct. And the mass of protons and neutrons are 1 for each. So 5. Okay. So again, from last week, the number at the top is mass number, which is the number of protons and neutrons. And then I have the symbol, and then I have the atomic number, which is the number of protons. Okay. Sometimes the numbers are written on the right, sometimes the numbers are written on the left of the symbol. But they represent the same thing, same element. Okay. Most atoms are stable. So when we look at in the periodic table, all those elements are, the numbers given are when it's stable. However, radioactive atoms are not. Okay, they are unbalanced and unstable. There is some of it which are unstable and unbalanced, and when it's what that basically means is that these numbers, the atomic number, will not stay the same.
So it's like uranium,
Yeah.
like
Correct.
uranium, like uranium,
Yes.
the ore.
Correct. Yes. So what happens to radioactive substances, radioactive atoms, is the atomic number will change as they go through a certain process. Okay? Okay. So why, when they're unstable, when they're unbalanced, they want to become stable because that's their ultimate motive. So what they do is they achieve this by giving out energy. They emit energy, and they give out, that energy is in the form of radiation. So basically unstable atoms, they give out radiation. Why? Because they're trying to become balanced, they're trying to become stable, because that's their goal. But in the process of becoming stable, they give out radiation. Radiation is a type of energy, so they give out energy, and that's in the form of radiation. Okay. Okay, so hang on, someone has entered. Okay, so sometimes it's a small amount of energy, so small amount of radiation. Sometimes it's a large amount of energy, it's a large amount of radiation. So can you all think of any examples of what do you think can emit radiation or can give out radiation?
Television.
Television, yeah.
Uranium.
Okay, the atom itself.
Weapon fallout.
Yeah.
Medical equipment.
Yes.
Cosmic rays.
Yes.
Microwave.
Correct. So actually, right, a lot of things around our houses, in our houses, they emit radiation. It's just that it's either we are not aware of it, or it's too small that it won't cause harm. I mean, if let's say you had something that emitted a lot of radiation, I don't think we'll be alive by now. So there's stuff, the normal household appliances that emit radiation, they emit in small amounts. So we're not really affected by it. Okay? So we will look at some of these examples, hopefully today lah. Okay, we'll see how we go with time. Okay, how many types of radiation are there and how are they different? So this is what we're going to look at today. So the first radiation is alpha radiation. So there's 3, alpha, beta, and gamma. These are the 3 types of radiation we're going to look at today. Okay, so we're going to look at alpha decay first, then beta, and then gamma. Okay, so alpha decay, what happens is, if you look at this, we have an atom, and then what happens is, okay, what do you notice from this and this? What is the difference here? Can anyone see what the difference is?
The proton,
Atomic number.
the total
Yeah.
of proton and neutron number.
Yes, so the atomic number at the bottom is different. Okay, so what is an alpha particle? Okay, so alpha particle is basically helium with an atomic number of 2. Okay, so I have an unstable nucleus. Remember, it always starts with unstable, trying to become stable. And then a new nucleus is formed. And in that process, radiation is given out. And this first one is radiation in the form of alpha particle. Okay, so alpha is an atom, when an atom decays into a new atom and emits an alpha particle which has 2 protons and 2 neutrons. Okay, alpha radiation is the nucleus of a helium atom traveling at extremely high speed. So when we're looking at alpha radiation, we're looking at a helium atom being released at extremely high speed. Okay, so alpha particle, alpha radiation, we're looking at helium, which has 2 protons and 2 neutrons. Okay, so far anyone confused or have any questions?
No, sir.
No, Chair.
Okay. So if you see, okay, so I have, this is the second one, beta particle, so beta decay. Okay, so what happens is for beta decay, I have electrons being released. So for alpha decay, I have helium being released at extremely high speed. And for beta particle being released, basically we're looking at an electron being released. When an electron is released, the new atom that is formed is automatically of a positive charge. Okay, look at it now. I have an unstable nucleus, remember always unstable, and then I have a new nucleus formed and I have beta particle being released. And a beta particle is when a neutron changes into a proton and an electron. The fast moving high energy electron is called a beta particle. So what happens in a beta decay is a neutron changes into proton and electron, and automatically when you have an electron, the electron will move because electron is a moving element of an atom. So this electron is moving really fast with high energy. So this is when a beta decay happens, when a neutron changes into a proton and an electron, and the electron is released. I have
can
a
I go
negative
toilet?
charge being released. Okay,
Can I go toilet?
can. Okay, so that we looked at alpha, we've looked at beta, and now we have gamma. Okay, so you see when a gamma is released, the atomic number is still the same. So the atomic structure doesn't fundamentally change when gamma ray is released. Okay, again, unstable nucleus, new nucleus, and I have gamma radiation and some sort
So
of.
it just remain the same, but it just emitting a gamma radiation.
Basically, gamma radiation doesn't cause any changes. Gamma radiation, which is when the unstable nucleus becomes a new nucleus, it might emit maybe an alpha or beta particle. But when gamma radiation is released, it doesn't affect the atomic structure of the nucleus.
Then how it's going to wear off if it
So,
doesn't change?
okay, we'll look at it. So the atom itself doesn't change. Okay, so basically gamma radiation is when an unstable nucleus becomes a new nucleus. It's either alpha or beta decay that happens. But what happens is sometimes there is an extra energy per se that is being released. So that is gamma radiation. So this new nucleus will have a change due to the change in beta and alpha decay, but it won't change due to the gamma radiation being released. If there is a change in the structure, it's because either there was an alpha decay or beta decay that happened. But if let's say gamma radiation is also released, that gamma decay will not affect the structure of the new atom that is formed. If it's changed, because it's probably there was another decay, there was alpha as well or beta decay. So gamma radiation does not affect the structure of the atom.
Right.
And gamma radiation is part of the electromagnetic spectrum that we looked at before in previous classes. It has high frequency with very short wavelength.
Wait, very short what?
Wavelength. And
Wavelength.
it has
Oh.
high frequency. Okay. So, type of radiation, symbol, what it is made of, how far will it travel in air, and what stops it. Okay, we're going to look at a few of these elements. Okay, very quickly, recap. If you want, you can take down this. I will stop here for a while. You can take this down if you haven't taken down notes from previous slides. So I have alpha, beta, and gamma radiation. Alpha, high-speed helium nucleus being emitted. Beta is high-energy electron. Gamma ray is after an alpha or beta decay happens. There's a surplus energy, an extra energy being released. So that is gamma radiation. It has high frequency and short wavelength. So I'll just pause here for a while for you all to take down the summary of what we have done so far. Anyone has any questions so far?
No, sure.
No, sure.
Okay, anyone still copying? Can you let me know?
I'm still copying, sure.
Okay. Okay, for those of you who are done copying, you can just flip through your textbook, page 328 and 329. Those are all the things that emit radiation, that needs radiation, where radiation is helpful. So sometimes we think of radiation as a bad thing, but there's a lot of useful, a lot of benefits of radiation. There's a lot of examples here. You can have a look at those. It's on page 328 and 329 of your textbook. In smoke detectors, to measure thickness of something, medical diagnosis, like all your x-rays and all these things, they're all useful. Food irradiation, sterilization, when doctors, when they do a surgery, when they perform a surgery, they use all these tools, right? They do a surgery on a body, and then the next surgery, they have to make sure they have sterilized the equipment, because let's say the surgery before, the person has been infected with the virus or anything, they must make sure that it doesn't infect the next person who's going to have their bodies being done surgery to using those equipments. So they really sterilize the equipments, because if not, they have to throw everything away, which is wasteful. So they sterilize the equipments properly. So they use radiation. You can't just dip it in hot water. You know, I mean, you go Chinese shop, you can dip your spoons in hot water, but when it comes to stuff like this, you need radiation to kill the virus that is harmful. Okay, can I move on to the next slide?
Still copying, Chair, but I'm at gamma radiation.
Okay. Anyone else still copying? Okay, still copying as well. Okay. Mute your mic, please. Thank you.
Oh, forgot about that. Sorry.
Justin, are you back?
What page are we supposed to open?
Huh? Sorry?
We using textbook.
No. I just stopped at the slide here, but we are on page 321. 322 actually, of your textbook.
Thank you,
Okay.
Chair.
Okay. Everyone done copying? Those who wants to copy? Zinnia done?
Yes, you're done.
Yes, sir.
Okay. Cedric?
Done, Chair.
Okay. Let's move on to the next one. Okay, so alpha, beta, gamma, this is the symbol. What it is made of. Beta, high-speed electron. So gamma is basically just a high energy wave. High frequency, high energy wave. Alpha is helium nucleus, 2 protons and 2 neutrons. Okay. So they all have different properties. Okay, they all travel in different distances, different strengths, and they are stopped by different materials. So these radiation, right, these radioactive materials, they can be stopped, but they must be stopped by different materials. There are some materials that they can penetrate through and some materials that they can't. So if you were to stop this radiation, there are different materials that you can use to stop this radiation. Why they have different materials to stop them? Because they travel at different speed, they travel at different strengths, they are able to travel at different distances. Some of these radiation only travel, one of it travels shorter than the other. So it might not reach as far as another radioactive substance. Okay, so look at this. So basically, let's say I have 3 sheets here. Okay, so
Teacher, you're lagging.
wait, just a moment. Now, okay?
Now okay, now okay.
Okay, so I have thick lead, I have aluminium, I have paper. So the first one is paper, the white one paper. Second one aluminium. Third one is thick lead. So which one can penetrate? Between gamma, beta, and alpha? Which one can penetrate through which one? Anyone want to guess?
Alpha got blocked by paper, beta got blocked by N and then grandma got blocked by thick lead.
Yep, that's right. So if I were to have alpha, beta, and gamma will be able to penetrate through even thick lead. Why? Because it is traveling, it has high frequency. Okay, beta until aluminium, then it cannot pass through aluminium. Alpha, it can pass through paper, and that's about it. Okay, so in this case, alpha is the, so to say, safest, in the sense that it can be stopped by a paper. Okay, so this is just another picture. Okay, so how far will it travel? Alpha, a few centimeters, beta, meters, gamma, many meters. Okay, what stops it? The air, paper, beta is aluminium, gamma is thick lead and concrete. Okay, so I would advise you to take this down. So I give you all some time to copy this down, just so that you all have a summary of a picture of all these types of radiation. What
Chad,
their properties are. Sorry?
the table is on page 322.
Oh, okay. Okay, if you don't want to, if you're going to refer to the book, then okay. Anyone who's going to copy?
Yeah, I took picture of it. I'll copy later.
Okay. But the table is not the same though. But
Yeah.
it's okay. You can always look back if you want to copy down. You can. But if anyone copying now, then I will wait for a while.
No,
copy.
Chad.
You're copying? Okay, we'll just wait for a while for those who want to copy now.
So I took a picture ni.
Okay.
So I'm done.
Done? Okay. Let's move on. Okay. So very quickly, if you want to answer, please raise your hand. Do you all know how to use the raise your hand feature? It is under participants or chat, if I'm not mistaken. And then you raise your hand, okay? So we don't have so many people talking on top of each other. Okay, what do you call the center of an atom? Okay, Justin?
Which is it proton? Hey, sorry, neutron.
No, not quite. Okay, CK. CK, you can unmute yourself.
Nucleus.
Yes, nucleus. So nucleus contains the proton and neutron. Okay, the center itself is called a nucleus, but what's in it is a proton and a neutron. Okay, next. A stable atom has, okay, Daman,
Equal number of protons and electrons.
Equal numbers of protons and electrons. Okay, how many types of radiation are there, or at least how many types did we look at today? Kezia?
3.
3, okay. Radiation is emitted from Mushiga. Unstable atoms. Okay, an alpha particle consists of Kezia?
2 protons and 2 neutrons.
Yep. Okay, beta radiation is Edmund?
Sure who?
Edmund?
Sure the high speed electron.
Yep. Next, gamma radiation. CK?
C, a wave.
Yep. Alpha is stopped by Daman.
The paper.
Paper, some more?
Air.
Yep. Oh, and yeah, actually it's all four, because if it gets stopped by paper, it also gets stopped by aluminium and lead. Does that make sense?
Yeah.
So if it's going to be stopped by paper and air, that means it can also definitely be stopped by lead and aluminium. Okay, beta is stopped by Kezia?
Aluminium and concrete.
Yep. And
Lead.
yeah, aluminium, concrete, and lead. Gamma is mostly stopped by CK?
So doesn't it like pass through all?
Yeah. But it's mostly stopped by, it can be stopped by what?
B, thick lead.
Yeah, thick lead. Okay, so we have covered structure of and properties of atoms, 3 main types of radiation, and their structures and properties. So now we're going to look at, very quickly, the ionizing properties of radiation. So we're going to look at the next part, which is ionization. Okay. Okay, what does ionizing radiation mean? It means when a charged particle comes near another atom, okay, it can pull electrons off the atom. That's basically the concept behind ionization. So ionizing radiation is basically when a charged particle comes near another atom and it can pull the electrons off the atom. Okay. This slows the particle down. And then the atom is then called an ion. That's why ionizing radiation. If it has lost an electron, it will be a positive ion. If it has gained an electron, then it will be a negative ion. Okay, so we're looking at when a charged particle comes near another atom and the number of electrons is affected. So if it loses an electron, it will become a positive ion. Because when it loses an electron, now there is more there's more protons, which means it will become positively charged, which is why it will become a positive ion. If it has more electrons than protons, then it will become a negative ion because there's more negative charge. So they are being ionized either positively or negatively. Okay, so when radiation collides with neutral atoms or molecules, it alters their structure by knocking off electrons. This will leave behind ions. This is what we call ionizing radiation. Okay. So I have a neutral atom, a stable atom, and suddenly radiation hits. The electrons get knocked off, they produce positive ions. Okay.
Wait, sure. What knockoffs again?
Electrons gets
Oh,
kicked out,
okay.
gets released. So when electrons leave, they automatically have more protons. So which means it becomes a positively ionized particle, positively charged particle. So what forms of radiation can be ionizing? Only a charged particle such as an alpha or beta particle can be ionized, can be ionizing. Okay, what about gamma? Gamma has no ionizing power, but it is still the most powerful radiation that passes through most objects. Okay, it doesn't have ionizing power, but it's still the most powerful. Okay, then there's something called background radiation. Okay, where does radiation come from and what are the sources of radiation? Okay, these are, just now you all answered a few things, natural and man-made resources that give about radiation. Okay?
Like microwaves?
Yeah, microwaves, TV. We'll look at later on. You'll be surprised at what are the things that actually give out radiation. Okay, very quickly to wake you up if you're half asleep. A neutron walks into a bar and asks the bartender, how much for a beer? What does the bartender say?
No charge.
That's right. For you,
That
sir,
you can
no
afford.
charge. Okay, because
Correct.
neutron, no charge. In case you all didn't know that.
Oh,
You all don't get
Okay.
it. Okay. So, background radiation. Radiation is always present in the environment. We call these background radiation. Okay. There are many sources of background radiation, natural and man-made. So naturally we have cosmic ray, food rocks, radon gas. Man-made we have hospitals, nuclear bombs, nuclear power stations, and accidents. Accidents also give out radiation. Your phone gives out radiation. Your phone charger gives out radiation, which is why they say don't sleep with your phone right beside your head. So if you all are doing that, please do something about it. Okay, it's very dangerous. Long term is dangerous. Okay, so these are the things we looked at, and then let's quickly look at this. This is just a breakdown of how much radiation each element gives out. Okay, so radon gas gives out the most, and then we have food, cosmic rays, gamma rays, medical, and nuclear power. Okay, this is background radiation, radiation that's already present.
wait, what is radon gas?
It's a type of gas now. It's a type of gas. Let me see how I can explain it to you. Just give me a moment. So it is something that is already present. Okay, already present in the air. You can't, it's odorless, you cannot smell it or anything. It just is naturally present in the atmosphere. Yeah. It's just a type of gas that is present in the atmosphere. Okay.
Okay.
So 13% is man-made and the rest is naturally present. Okay. Okay, isotopes is the next one, but we've already done isotopes, so I'm not going to cover isotopes. Okay, so let's just look at this. These are just some of the things that give out radiation. And this is how radon gas enters the house. Radon in groundwater, well water, in the soil. It's basically everywhere. It's just that we're not, I mean, it doesn't affect us much, but it's in abundance in our environment. Okay. And then for medical, when you go for MRI, CT scans. There's a lot of the scans, right? They don't allow, sometimes you have to go in yourself because there's a lot of radiation. And if let's say you are going for a check, then fine, radiation needs to go through your body. But sometimes for certain checks, even the doctor doesn't go in. You go in there by yourself and then you come out, because the doctor doesn't need any radiation in the body. So it's unnecessary radiation to the body, because radiation can kill your cells, your body cells, which is why when you do a scan, right, you cannot simply do scan like, oh, I feel like doing an x-ray today, and then two days later, oh, I feel like doing another x-ray. Like, you can't do that, because when radiation goes into your body, it can kill your body cells. So usually they say you wait a while before the radiation dies off. The radiation needs to die off first, then only you can, you know, if not, if you just keep putting radiation into your body, then it will kill the body cells.
Sure, but how they know when the radiation die?
There is a time frame for each type of radiation to die off. So different kinds of radioactive substance have different time before it dies off, depending on the dosage and all that. So that's why sometimes when you go for an x-ray checkup, right, sometimes the doctor will ask you, okay, when was the last time you did an x-ray?
Last year.
Yeah, so they will ask you. Why do they ask you? Is because they want to make sure that you don't do 2 x-ray checkups very close to one, unless it's really necessary. You know, sometimes there's an accident case, and then the patient needs to go through a few types of scan, because they want to check where is there internal bleeding, are bones broken, are muscles torn, and all that. So you have to go through different scans. That's a different case. But if you're perfectly healthy and you just want to do a regular checkup, there's only so much radiation your body should take at one go. You shouldn't take a lot more than what your body is supposed to take, because it's harmful. Okay?
Okay.
So these are even construction sites, nuclear power plants, all these things, they all emit some sort of radiation. Okay? So sometimes if you go to certain construction sites, they put the sign there, the radioactive sign. So those are places that are...
Is that from Chernobyl?
I'm not sure lah.
How are we supposed to know, dude?
I wouldn't know. For all you know, it's like somewhere in Malaysia. I really don't know. But these construction sites also very highly radioactive. So yeah. Okay, another one. An atom bumps into a friend in the street and says, "I've lost an electron." The friend says, "Are you sure?" What does the atom say?
I'm pretty positive.
That's right, because they've lost an electron.
Wow.
Oh, great.
Nice.
Oh yeah.
Okay. Okay, so these are just, what does the term ionization means is when charged particles are produced, either gaining or removing electrons. Remember, if you gain electrons, you become negatively charged, because now you have more electrons than protons. So you become negatively ionized. If you're removing electrons, you become positively ionized, because you have more protons than electrons. Okay, what types of radiation cause ionization? Only alpha and beta, not gamma. But gamma is still the one with the most energy and can penetrate through most things compared to alpha and beta. Okay, isotope, something we looked at last week, atoms of the same element with a different mass number. Okay, what is radioisotope? When radiation and isotopes combine, is an isotope of an element which emits nuclear radiation. That is radioisotope. Okay, so far anyone has any questions?
No, Joe.
No.
So I cannot see number 4.
Why? What is a...
I mean, the whole thing.
Okay, I'll just read it to you. So it just basically says that, so I have isotope, which is what we looked at last week, different number of neutrons. Radioisotope is when radiation and isotopes combine, which means it's an isotope which emits nuclear radiation. So when an isotope gives out radiation, we call them radioisotopes.
Okay.
Okay, I'm not sure why you cannot see number 4. Can everyone else see
Because
number 4?
the thing blocking down there.
Yes.
What is blocking?
I have no idea.
Okay,
So now mine.
maybe I think later in the video you can see once I upload the video.
Okay.
Should be able to see. Okay, so again, like I said, radiation can be harmful or beneficial. It doesn't mean that if it's radiation, it's a bad thing. There's also many benefits, many useful things about it. Okay. Okay.
Yeah, don't they use radiation to clean those medical things
Yes.
after they do surgery?
Yes, correct. Radiation is also used to kill cancer cells. So when cancer patients go for chemotherapy, they're using radiation to kill cancer cells. That is why, right, chemotherapy can also make someone weak. Because as much as chemotherapy is killing the cancer cells, you're allowing so much of radiation into the body, which makes the person weak. That's why there are all these side effects. They either lose their hair, their skin becomes dry. So these are all side effects of having so much radiation in your body. But at the same time, it kills the cancer cells. So which is why there is a positive and negative to it. So some people, when they have cancer, they choose not to do chemo. Why? Because there's so much of side effects. They become weak and all. Some people, they do chemotherapy because why? They do want to kill the cancer cells. So again, good and bad to it, which is why they haven't found like a cure to cancer which doesn't make the person suffer in the process of getting therapy. Okay, so what is the benefit of using radiation as opposed to operation to remove a tumor? What do you think is the benefit of that? Why use radiation instead of removing a tumor?
Wait, because it can penetrate through the skin and go straight to the cancer cells.
Okay, so that's one of it. So when you operate, you need to open up the body. You need to open up the body, which means there is higher risk of contamination, higher risk of things not going the right way. Whereas radiation, it just penetrates through. So you don't have to imagine having to do every time you, because cancer cells, they spread. Okay, so, and the moment you remove one, by the time you remove one, it's already spread to another part of the body. If let's say it's spreading really fast, that's its stage for cancer. So imagine having to remove the cancer cells every time. Then does that mean you go and operate yourself every time? No. I mean, it's a bit difficult to do. Whereas, so radiation, it penetrates through the skin and it hits the tumor cells inside. So you don't need to open up. You don't need to open up a body every time you want to remove cells, because cancer cells spread and you cannot operate someone all the time. Imagine being operated 2 weeks once. You know, it's not, it's hard. It's I don't even think it's possible. The body cannot take it, even if it's a healthy body. Okay, you won't be able to take it, because by the time you recover and everything, and then you do another operation, then over time it just gets bad. Okay, so those are some of the benefits. And then sterilizing medical equipment, blockage in a kidney, so all these things, to measure the thickness of paper, to measure the thickness of things, the alarm system, all these things, they use some sort of radiation. Okay, so that's pretty much it for this part. Okay, I'll give you all 5 minutes break, then you come back. Then we will continue a little bit more on half-life and radio decay.
Okay, sure.
Okay, sure.
Okay, so I give you all 5 minutes. Just quickly go and If you want to get some water, you want to mix yourself a drink, you want to go to the toilet, quickly go and then come back. Come back at 10 o'clock and we'll continue.
Sure.
Okay, everyone back? Or not yet?
Sure,
I'm here,
back.
Cher.
Okay. So Cedric is here and Edmund is here, right?
Sure,
Sure.
here also.
It's Justin.
Justin, oh, you and Edmund sound so similar.
Sure, Edmund is also here.
Oh, okay. That means, okay, fine. They all sound very similar. Huh? Who is your
Yeah,
deep?
Yeah, very sure.
Okay, never mind.
just so if I say anything like make you angry, you can scold Justin.
Not that way.
Chill, chill.
Okay, is James back? No.
Yeah.
Oh, he's back. Cedric is back. CK, are you back?
Always blame
Yeah,
Justin.
sure.
Okay, Daman? Okay, Daman not yet. Desri?
Yes, sure.
Diksha?
Yes, sure.
Okay. Edmund is back. Justin. Kezia?
Yeah, sure.
Okay. Justin is here. Yonghum? No, Yonghum not here. Mushiga?
Did he join today? He didn't join today.
He joined just before we ended the first half.
Oh,
Mushiga is back. Zinia?
Yes, sure.
Okay, so Daman is not back yet.
I'm back, sure.
Okay, you're back. Okay, the rest are here. Okay, let's continue with the next one. Just give me a moment. Okay, so next part we're going to look at is called half-life. Okay, so half-life is basically, you know, when we talked about how when you do an x-ray, you have to wait a while before you do the next x-ray because we want to give the the radiation time to die off. So this is what happens. This is essentially what happens when it decays. So decay is basically it's trying to become stable. So radioactivity is when an atom is not stable. So it decays and decays and decays until it becomes stable and doesn't give out radiation anymore. So every element, like I said previously, has a different time of which they will die off. And when they die off, sometimes after a certain time, they maybe die off a little bit and then a little bit more before they completely die off. So that's what we're looking at essentially when we talk about radioactive decay. Okay, this is on page 325 of your textbook. If you wanna look it up. Okay, so when we're looking at radioactivity, basically different radioactivity take different time before it decays. So what we're looking at, the time element that we're looking at is called half-life, which is essentially the time taken for half of the atoms to decay. So let's say you start with 20. So for it to become 10, which is half, how long does it take? So time taken for half of the atoms in a sample to decay. Okay? So let me just open this. Everyone can see the slides?
Yeah, sure.
Sure.
Yeah, sure.
Yes, sure.
So we cannot predict when any particular nucleus will decay. Okay, we cannot just predict just like that. Okay, we don't know. But there is a fixed chance that any atom will decay in the next second. Okay, how much it will decay, that's another story. But there is a chance that an atom will decay in the next second. Okay, because they're constantly trying to be stable. So it's like an ongoing thing. It keeps happening. So 1/10 decay each second. So 1/10 gone, and then another 10th gone, and then another 10th. Okay, so every second, 1/10 decay. Okay, so here is usually a graph that you'll always look at. This is called a decay graph. Okay, so if you see on the left-hand side, on the vertical axis, I have the number left, number of the radioactivity left, and then down is the time. So it starts with 100, and then it drops down to 40. Sorry, it drops down to 0 at 40 seconds. So after 40 seconds, then it drops down to 0. Okay, so from 100, if you just look at the graph, yeah. Okay, one thing to remember, the time for the number left to half is always the same. Okay, this is what we call half-life. So if we look at this, 100, to become 50, how long did it take? How many seconds did it take? For 100 to drop
It takes up.
50.
It takes about 13 seconds.
13. How did you get 13?
By 50 divided by 2, that is half. So technically, it is 25, and then you
100.
just divide by 100.
Around 5.
Oh,
Yes,
then
correct.
then you get 50. Then if you divide it by 2.
Correct. So 100 divide 2 is 50. So it's around 5 seconds, or slightly more than 5 seconds. So it's here, it's the red color, the red one here. So for 100 to drop down to 50, which is half, it takes about 5 seconds or so. So this time, this 5 seconds is called the half-life. So when we look at half-life, we are looking at the time taken for half of the atoms in a sample to decay. Okay, so we start with 100. When it comes to 50, how long did it take? That's the half-life. If we start with 200, okay, how long did it take before it became 100? So we're looking at half the amount of what it started with. Okay, so we're looking at the time taken for half of the atoms in a sample to decay. And then if you look here, from 100 to 50, it's about 5 seconds or so. And then from 50 to 25, it's about another 5 seconds or so. And then 25 divide 2 is about 12.5. So around here, another 5 seconds, and then another 5 seconds. So the time taken for the number left to half is always the same. Okay, so if it's going to be, for it to become half, it will be 5 seconds. So every time it becomes half, it will be another 5 seconds, another 5 seconds. So that's what they're trying to say. The time for the number left to half is always the same. Okay, so this time is called half-life. Okay, let's look at a graph and see what's the half-life. Okay, this is iodine 131. What is the half-life of this unstable atom? Roughly, I can give me a rough estimate.
Is it like 200?
Yep, it is slightly before 200. So let's see.
Is
Let me
it
Yeah.
180?
take a pen. See if I can draw. Take blue, green. Okay, so this is, so 100, the half of 100 is 50. So 50 is around
It's
here.
185.
Yeah, so let's see. Let's see if I can draw dotted lines. Hits here, and then it goes down. So this is 100, this is about 150. 120, 140, 160, 180. Yeah, about 185. So it's about 185, in this case, hours. So it takes a while for iodine-131 to decay to half of its amount. Okay, so remember, when we look at half-life, we're looking at the time taken. Okay, so in this case, we started with 100, so we want to look at 50, because half of 100 is 50. Okay, anyone still confused on the concept behind it, or still don't understand before we move on? Okay, I'll take that as a no. Okay, in this case, they put 192. Again, this graph is not to scale, so that is their answer, but it's around there. It's around there. Okay. Okay, let's look at this one. Iodine 135, slightly different. How long does it take for it to?
7.
7. Okay, let's see. Okay, so this is about 50 because we start from 100, so 50. Okay, I hit the graph. Yep, it's about 7. So 7 hours. Okay. So this is like less than a day. Okay, so if we were to compare the half-lives of both, iodine 131 is the red color, the blue one is iodine 135. It's very different. One takes about 7 to 8 days and the other one takes about 7 hours. Okay, so different, like I said before, different unstable atoms will have different times as to which they decay or die off. Okay, so by the time it becomes, so when it's 50, it's about 7 hours, and then comes to 25, and then by the time it has no activity at all, it's already a different amount of time. So it takes a while. Some of it takes years. That's why sometimes when a nuclear bomb happens in a specific place, right, that area for many years, it cannot grow any crops. They cannot grow any put like a water plant there or anything like that, because the radiation is still so high there that the soil and the ground is now
Contaminated.
yes, contaminated, so it cannot grow crops. Because even for soil, for plants, there needs to be a certain pH value. There needs to be a certain amount of elements that allows plants to grow. So when all these things are disrupted, when it's contaminated, the plants cannot grow. So sometimes the land is just bare for many years. Okay, because it takes a long time. So when
It's gonna be so when you're like a nuclear explosion or a nuclear accident happen in that area, the plant life will deteriorates, right?
yes,
Like
and
in a rapid rate.
correct. And the thing is, when there's no plants, especially if the people around there has been surviving on their own farming and their own crops, it's very difficult for them to sustain alive there, because they have lost their source of income, their source of food and all that kind of stuff. So usually what they do is they relocate these people to another place, because if there's not going to be crops for many years, then they won't be able to survive there. So they relocate them. Why sometimes with nuclear explosion, even if people are maybe 1 kilometer away, 100 meters away, 200 meters away, why do they still die? Because radiation can also pass through air. So some people die. Sometimes it's just the land that is affected. So yeah, so all these things, and then it takes a long time now before it becomes stable again and that place is able to sustain lives again. Because then you start from scratch when you start building your crops and you start fermenting the soil and all these things. Okay. Okay, so a short half-life, very quickly, this is elements of the graph that you must be aware of. So you plot sets of data on the same graph, you see the significance of different half-lives. A short half-life okay, means the activity decreases much more quickly. Okay, short half-life means, let's say, between 7 hours and 7 days. The shorter one just means it decreases much more quickly. Between 7 hours, it decreases. Another 7 hours, it decreases. So the radioactive source becomes safer sooner. So the shorter the half-life, the faster it decays. So it becomes safer much sooner. Okay? So when used as a treatment for cancer of the thyroid, the longer-lived iodine 131 is used. Now, why, when you want to cure cancer, when you want to treat cancer, why do they use a radioactive substance that takes a longer time to die off?
Because to
cancer
kill
cells
off
doesn't
the cancer
multiply.
cells so they can't reproduce.
They can't multiply.
Something like that.
Yeah.
Something like
They don't multiply as fast. It takes a longer time so that the radioactive substance can stay in there for a longer time so that they can target more cells at one go before they die off. Okay, but like I said, there is a downside to it. Okay. Now, cesium-137 was released into the atmosphere where the Chernobyl nuclear reactor exploded in 1986. Should we still be concerned? So this happened in 1986. Now it's 2020. Should we still be concerned about it, or has it completely died off?
No.
still concerned. I'm still concerned about it.
Okay, so it's still there. Okay, so cesium-137 has a half-life of about 30 years. 30 years means for it to decay to half the amount, it takes about 30 years. Okay, traces of isotope washed out of the clouds by heavy rain can still be found in the soil of the Welsh Mountains till today. It emits beta radiation, so yes, we should still be concerned. Sheep from these Welsh hills are brought down to clean pastures so that the cesium they have taken in with contaminated grass can work its way off their system before the meat is eaten. Okay, so even when animals eat them and everything, they also get contaminated by it. Okay, so this is when it decreases in size by half-life from 16 to 8, become 4, become 2, become 1. So half, which is 1/16. So after one half-life, half goes off. Another half-life, quarter goes off, and then it keeps. It's like that lah. That's how we calculate it. After 6 half-lives, so it's 6 of halves. So half times half times half times half, 6 times. Okay, true or false? The activity of a source reduces to 1/16 of its original value after 4 half-lives. Is it true or false? So 4 half-lives, does it reduce to 1/16?
False.
True.
True.
Yeah, because after 4 half-lives means half times half times half times half, 4 times. So half times half is 1/4. 1/4 times half is 1/8. 1/8 times half again, it's 1/16. The previous one, let me see. Yeah? So after 4 half-lives, it's 1/16. So it's true. The radioactive isotope sodium-25 has a half-life of 1 minute. So every 1 minute, it decreases to half. What fraction of it remains after 3 minutes?
1/8
1/8?
or 1/4.
1/8.
1/8.
1/8. Because 1 minute is half, 2 minutes is quarter, 3 minutes is 1/8. Okay, let's see. The medical tracer technetium-99m has a half-life of 6 hours. Okay, a sample gives a count rate of 2,400 counts per second at 11 a.m. on Monday. how many half-lives will it take for the count to drop to 300 counts per second? How many half-lives?
No, no.
Is it sure, are they asking for the amount of hours?
Now, how many half-lives? So is it
Three.
one
Is it
half-life?
3?
Yes, 3. Okay, so in this case, it will be 2,400 drop down to 300. So 2,400 to go down to 1,200, half, go down to 600, another half, and then go down to 300. So there are 3 half-lives here. 1, 2, 3. Okay, how long will it take for the count to drop to 300 counts per second?
18
18
hours.
hours.
18 hours. So 3 half-lives, each is 6 hours. So 3 half-lives means 3 times 6, which is 18. What day and time will it be when the count is 300 counts per second?
5 p.m. Tuesday.
5 p.m. Tuesday. How did you get 5 p.m. Tuesday?
So 11 a.m. then like you add 18 hours.
Okay, so it will be
Isn't it 5 a.m.
5 a.m.
Tuesday?
Oh yeah, oops, nice.
Okay. So 5 a.m. on Tuesday. Okay. Okay, let's see the next one. Xenon-133 is a radioactive gas used for diagnosing lung problems. In 15 days, its activity falls to 1/8 of its original value. What is its half-life?
Five days.
5 days? How do you get 5 days?
So like if 1/8 is 15 days, then like 1/4 is 10 days and 1/2 is 5 days.
Yep. So you can work on it backwards like that. Or to get 1/8, I have half times half times half, which means there are 3 half-lives in that. Okay, so 15 days, so 5 days per half-life, because 3 half-lives. So 15 divided 3 will be 5 days per half-life. Okay? Okay,
Yeah.
the half-life of, oh yes, someone call me?
No, sure, just understanding.
Oh, okay. The half-life of the radioactive isotope sodium-24 is 15 hours. A sample has a count rate of 240 counts per minute. Its count rate 60 hours later will be
15.
15,
30.
30.
Is it 15?
Okay, let's see.
Yeah, 15.
It is 15. Why 15? Because I have 15 hours for each half-life, and they're asking 60 hours later. So 15 to 60 hours will be 4 half-lives, which means it has decreased 4 times. So 240 to 120 is 1 half-life, 60 is the second one, 30 is the third one, 15 is the fourth one. So 4 half-lives it went through, so it will be 15 counts per minute. Okay, anyone confused? Anyone don't know what's going on, or unsure, or you want to ask some questions?
Roger.
No. Okay. Okay. Next, a radioactive isotope of silver has a half-life of 20 minutes. So every 20 minutes, it's decreasing by half the amount. A sample gives a count rate of 6,400 counts per second at 9 a.m. At what time will the count rate be about 200 counts per second?
So will it be 10:40
Okay, we have 10:40 as one of the answers.
a.m.?
Any other answers? Any other answers? No? Yes? Okay, how do you get 10:40? Kezia, can you explain?
From 600, I mean from 6,400 to 200, it's 5 like half-lives. So then you take 5 times 20, you get 100 minutes. And then the 60 minutes is just 1 hour. So you plus 1 hour, then you get 10, and then there's 40 minutes left. So it's 10:40.
Okay, let's see. I have 6,400. To go to 200, I have how many half-lives? I have 1, 2, 3, 4, 5 half-lives. So 9, and each is 20 minutes because half-life is 20 minutes. So 20 minutes here, 20, 20, 20, 20. So which is 100 minutes. So it will be 9 to 10, and 9 to 10 is 60 minutes. And then another 40 minutes will be 10:40 a.m. Okay? Okay, next one. A sample of a bone from a living animal contains carbon-14. Its activity is 80 counts per minute. The half-life of carbon-14 is 5,730 years. Wow. How old is an antler with activity of 20 counts per minute? So carbon-14, while you'll figure it out, carbon-14 is a radioactive substance that they use for carbon dating. Carbon dating is basically when you find a bone that has been there for a long time and you want to find out how old that bone is. Then you use carbon dating to find out how old that piece of rock is, or piece of bone is, or that skeleton is. So carbon dating helps with that. So a lot of archaeologists, they do a lot of this. They find these things and they try to figure out, trace back, okay, how
Sure.
long ago did something exist? Yes.
Is it 11,460 years?
Okay, how can you explain to me how you got that?
Uh, 80. Uh,
Sorry?
80 to 20 is 2 half.
Okay.
I take 2 times 5,730 years.
Mm-hmm.
I get the answer.
Okay, let's see. So correct, 80 to 20 is 2 half-lives. Okay, then 2 times 5,730, I get 11,460 years.
Nice.
Okay. So basically you want to find out, the first thing you want to find out is how many half-lives is in the whole process, in the whole time between the count that it started with and then it ended with. Okay, or and you want to see how many half-lives are there, and then from there you decide how long did it take, or when did something end, and things like that. So you always start with how many half-lives there are, okay, in order to go on to the next. Okay. Cobalt-60 sources are used for sterilizing medical instruments. It has a half-life of 5.27 years. So what percentage of a source remains after 10.54 years? how much remains after 10.54 years? If the half-life is 5.27 years.
Is it 25%?
25?
Can I go to the toilet?
Yes, can. Anyone has any other answer?
For some reason, I got 54%.
54%?
I just got
Yeah.
50.
50%? Okay, so let's see. I have from 100% to go to 50% is half, and then 50 to 25% is another half. So 5.27 years is one half, and then 10.54 years is another half. So you end up with 25% at the end. Okay?
Okay.
So you start with 100%. To go to 50% is 5.27 years. So that's half. And then another half of that to come to 10.54 is another half. Okay? After the activity drops too low to be used, the cobalt-60 source must be disposed of safely. If the source must be stored until its activity has dropped to less than 1,000 of its activity today, it would have to be stored for at least how many half-lives?
Ten.
10? Any other answer? Okay, let's go back to the question. I have, yeah, they just give me the half-life, so there's no other information. Okay, so basically they're saying this cobalt-60 source must be disposed of, but you only can dispose it of after it's come to a place where it's stable. Because if I just throw it away and it's out there in the open, it will affect people. So we must wait until, let's say, wait until it's stable and it doesn't give out radiation anymore. Okay, so we want to drop to less than 1,000 of its activity. Okay, so you have 1 of 1,000, which is 0.001, and then 1 divided 2 is 0.5. You keep dividing it until you get to 0.001, or in this case you have 0.000976, which is about 10 half-lives. So you keep dividing until you get to 0.001, because you only can dispose after 1,000 of the activity. Today means it starts at 100% lah. Okay, and then it's about 10 half-lives. Okay. Okay, how many years is this? So one half-life is 5.27 years. So 10 half-lives will be 52.7 years. Okay. So these are just some more extra questions. But that's essentially what we are looking at today. Anyone has any questions?
No.
No? Okay. Actually, I have one more part. 10:30, okay. I have one more part that I want to go through. Okay, these are just okay. just very quickly before we end today's class. Okay, nuclear reactions, alpha, beta, and gamma decay. So I'm just going to show you how formulas are written down. And it has to do with the number, the atomic number that is changing. Okay, it's not difficult to do. Okay. Okay, very quickly, yeah. So the atom, it consists of two parts. I have the nucleus, which has the proton and the neutrons. And then I have the electrons surrounding it, orbiting electrons. Okay. So these are things we know. All matter is made up of elements, example, carbon, hydrogen. Smallest part of an element is called an atom, and they have different numbers of protons. Okay, and when we look at the mass of an atom, we look at protons and neutrons. Okay, again, these are things that we know. Okay, I'm just going to skip all this part. Okay, there are many types of uranium. We've got isotopes of uranium. The nuclear number is changing. So for the first one, A is the top and Z is the bottom, okay? So my A is 235, my Z is 92, number of protons 92, number of neutrons 143. For the second one, my nuclear number is different. Why? Because my number of neutrons are different, but my proton number stays the same. Okay. Again, something that we already know. So most of the isotopes which occur naturally are stable. A few naturally occurring isotopes and all of the man-made isotopes are unstable. So they can become stable by releasing different types of particles, which we look at is the alpha, beta, and alpha, beta particles, and some of it gives out gamma rays as well. So this whole process of giving out these particles, they're called radioactive decay. And then we looked at the half-life, how much they decay over a period of time. Okay, so again, alpha, beta, gamma ray, helium nucleus, 2 protons, 2 neutrons. Okay, so let's look at this. I start off with element X, and then the decay happens. I end up with element Y with the helium atom, because when we are looking at alpha decay, we are looking at helium being released. So it's very simple. The top number, the left-hand side must equal to the right-hand side. Same thing for Z. The left-hand side must equal to the right-hand side. Okay, so I have an unstable atom, and then I have a more stable, and then alpha particle. Now, just because it goes through a decay, it doesn't mean that this particle is already stable. It becomes more stable than before, but it can keep on decaying. Okay, so I have radium, and I give out a helium particle because of alpha decay. So again, with this, how would I write the formula? So I start with radium 88, and then here I have 86. But why left and right is balanced? Because 86 plus 2 is 88. Here 222 plus 4 equals to 226. So the basic idea is the left must equate to the right when you're writing your equation. So when you write an equation, make sure when you add up the right, it must total up to the left. That's the main part, the essential part of writing equations. Okay. So for example, this one. What would the proton number of Y be?
$84.
Yep. And the nuclear number?
218.
Yes. So 218 and 84. Why? Because 84 plus 2 is 86. 218 plus 4 is 222. Okay. It's very straightforward. Okay. Next one. For X, what did it start off with, the nucleus? What is Z?
92.
Correct. And A?
234.
Correct. Okay. Very straightforward. Okay, this one. What is Z?
88.
Yep. And A?
36.
220.
226.
226. Okay, it's 84 and 218. I'm just adding up the numbers essentially. That's what I'm doing. Okay, beta decay. Beta decay, a bit different. Same concept, left equals to right, right equals to left. But now, beta particle is when a fast moving electron is emitted. So, which means we are looking at a negative charge now. Okay, remember just now, like I said, when neutron changes to proton, electron, and the electron gets released. Okay, one less neutron, but one extra proton. So the atomic number increases by 1 and the mass stays the same. Okay, this is an example. So it increases by 1, why? Because an electron is released. But if you see, 85 minus 1 is 84. The neutron doesn't change. So 218 and 0 is 218 lah. We're only looking at what changes is the proton number. So for example, this one, 85 minus 1 will be 84. It's now minus lah instead of adding. But it's the same thing, essentially the same thing. For this one, this is 90. So this is 91 because 91 minus 1 is 90. The up one again stays the same. Okay, try this one. What would Z of X, the proton number of X be?
81.
81, A?
210.
Yeah. Okay, how about this one?
84.
84 and 210. This one?
82.
82 and 214. Okay, I'm basically just 83 minus 1, 82. The thing that you must remember when you write equations is you must not forget things like -1, the 0. Although, yes, it doesn't make a difference. In this case, 214 plus 0 is 214. You must write these things because these things make a difference. Okay, last one, gamma decay. No charged particles like alpha and beta particles because they're just electromagnetic radiation with high frequency. So when atoms decay by emitting alpha or beta particles to form a new atom, the nuclei of the new atom formed may still have too much energy to be completely stable. So what happens? This excess energy is emitted as gamma rays. So after emitting all the alpha or beta particles, it may still have too much energy to be completely stable, even after doing all the decay. So this excess energy is in the form of gamma ray. And that's pretty much it. Okay, anyone has any questions?
No, Chair.
No?
No,
Everyone
sure.
okay?
Sure.
Yes.
Do we have, so the beta and the alpha the calculations, right?
Mm-hmm.
As is own.
It's just straightforward calculation lah.
Just straightforward.
Yeah, it's just straightforward like that. There's no
Okay.
like confusing formula or anything. You just have to make sure that the left-hand side is balanced out with the right-hand side. It's like for chemistry,
Okay.
you balance out the number of the elements, the number of each atom. In this case, you want to balance out the proton number and the nucleon number. Okay?
Okay.
That's all for today. I will upload this video online and then I'll upload some questions. And next week onwards, we will try and start doing our past year papers. So please make sure you have them with you, either printed or, and we'll just start practicing questions. If you have any questions on previous topics, so because I ended up giving you all questions from last year's topics as revision. But if you have any questions on last year's topics or anything, you can please prepare them beforehand, and we can go through it next week. If not, we will jump straight into our past year questions. Okay?
Teacher.
Okay,
Teacher.
that is all for
Teacher.
today.
Teacher.
Thank you. Have a
Thank you,
good day.
teacher.
Teacher.
Teacher.